Hi guys, I am back to talk about some of the foundational things about cellular respiration. And so this is going to include the concept of substrate level phosphorylation, so what it is and how it makes ATP. We're going to talk about redox reactions and what's happening as the electrons move. We're going to explain or talk about why energy must be released in tiny amounts. And then we're going to talk about the role of NAD+, what it does for the cell during respiration. So the first thing is substrate level phosphorylation. And so if you break down that word or those words, phosphorylation means to add a phosphate group to. Okay, so simply, for example, when we take ADP and we add a phosphate group to it to make ATP, that's phosphorylation. And when we're talking about phosphorylation in cellular respiration, that's exactly what we're talking about. We're talking about making ATP. I don't know why that's not focusing. Maybe I can get it to focus. And so when we talk about substrate, that word should look familiar to you from enzymes. So when you have an enzyme and it binds with something, so here's the enzyme, the thing it binds to and acts on is the substrate. So substrate level phosphorylation is simply where we have this enzyme, it comes over and it hugs ADP and a phosphate. So it just hugs them, pulls them close together. And it actually catalyzes that reaction. So there's the enzyme afterwards of forming ATP. And so this pops off. Okay? So when we say substrate level phosphorylation, all we're talking about is an enzyme is taking ADP and a phosphate group and putting them together to make ATP. There's nothing else going on. There's no redox reactions. There's nothing else involved in that phosphorylation other than the enzyme, and the substrate is ADP. Okay, so that's why it's called substrate level phosphorylation, because there's nothing fancy going on. That will make more sense when we talk about oxidative phosphorylation, or if you remember about oxidative phosphorylation, that there are other ways we can make ATP, and so this is just one way by using just an enzyme. Okay, the next thing we're going to talk about is redox. Redox stands for reduction, and what we're talking about is a reduction in charge and oxidation. Okay, so what happens is you have this atom, and there's the nucleus. Okay, you got your two little electrons on the top. I don't know, I'm just making up an atom. Okay. Okay, and so then we have another atom. And let's see, 1, 2, 3, 4, 5, 6, 7. All right, and this one just has one on its, and this is, what I'm showing is almost like making ions, but this is actually happening with molecules. I just don't have the chemistry, you know, where I can pull it right out of my head fast enough to draw out whole molecules. But what happens is this guy says, you know what, I don't really want this electron. I'm going to have it handed over to you. And when that happens, this atom goes from being neutral to being positive because it was neutral and it lost a negative. Remember, electrons have a negative charge. So if you're neutral and you get rid of a negative, you're going to become positive. So this one was oxidized. Okay? This one, because it took that electron, so it was neutral ahead of time, it took that electron, it becomes negative, it has been reduced. Okay? And so we see this like in glycolysis. We have glucose, and when it breaks into its two pyruvates, electrons are released, and those electrons are going to go to NAD plus to make NADH. So since it took the electrons, this guy was reduced. So NAD plus was reduced to be NADH, and the electrons came off of glucose, so glucose was oxidized. Okay? So I can describe redox reactions by explaining what happens when electrons move from one molecule to the other. So when the electrons moved from glucose to NAD+, that oxidized glucose and that reduced NAD+. And we know it reduced it because, I don't know what is going on with my, there we go, because it was positive and now it's neutral. And so positive is the most positive, neutral would be, where my hand, there we go, the next negative, and then So if you're going from positive to negative, it would be positive, neutral, negative. So going from positive to neutral is moving in that negative direction. All right. The next one, I can explain why energy must be released in small amounts. Okay, so let's take glucose for example. Glucose is like a huge amount of energy. So if you compared it to money, it's like a $100 bill. And when you break that down, you don't want, imagine if when you broke a $100 bill, like you went to the store and bought a pack of gum, that money just exploded, well, and flew everywhere. Well, I don't want a $100 bill to explode and go everywhere. I'd rather like a dollar bill. And so that's why I would use ATP, because when ATP is broken down and that energy is released, it's a small amount of energy, and so the cell can manage that. But when glucose is broken down and all of that energy is released at one time, it is going to be released in the form of heat or light. That's usually how energy is released in these kinds of situations. And that is going to literally kill the cell. It's going to vaporize it. Like, phew, it's gone. And so we have to break that glucose or whatever it is we're breaking down and getting that energy, doing that exergonic reaction. We have to do it in little tiny baby steps. So we lose a little bit of energy. Let's do a capital E for energy. Okay, then we do another step and we remove a little bit of energy. Okay, so if we do, if we do it in baby steps, we lose little bits of energy at a time. If we did it in one big step, we would lose a ton of energy and the cell would die. It would burn up. So we need to do it in small steps just to protect the cell. All right, and the last thing is I can explain the role of NAD+ in the cell. We've already talked a little bit about it, but NAD+ is what we call an electron carrier. Some people like to call it an electron shuttle or an electron taxi. Because if you think about what a shuttle does or what a taxi does, or nowadays what Uber does, it is going to pick up electrons. So in this case, it's picking up electrons from glucose, and it's going to go drop them off at the very last step, which is called oxidative phosphorylation at the electron transport chain. And so it is literally the job of NAD+ is to pick up electrons and the energy that they contain and move that energy and those electrons to a different site. So they really are shuttling them around the cell, or Ubering them around the cell, or taxiing them around the cell. It is reusable. So when NADH gets over here, it's going to drop those electrons off. It's going to go back to being NAD+, and it'll come back over here to glycolysis or the citric acid cycle or pyruvate oxidation or whatever and pick up more electrons. And so that's just literally what it does all day long. Picks up electrons, drops them off. Picks up electrons, drops them off. But in the course of doing that, it's moving those electrons around the cell, in this case around the mitochondria. And so that those are all the little foundational things that you need to understand to really have a better grasp of cellular respiration. So I hope that helps. If you still have questions, let me know.